Elemental aluminium is the most abundant metal in Earth's crust, and makes up approximately 8% of the total crust mass. In civil and construction applications, an aluminium alloy is most commonly used, and the type of alloy varies depending on the requirements of the structure. Aluminium has been in use since the mid-19th century, however production prices have drastically decreased over time. This fact, coupled with the sheer abundance of the metal, means that aluminium is the second highest used metal in the construction industry, only falling second to iron. The Australian aluminium mining industry is one of the largest in the world and is a $50 billion industry. Australia is also the world leader in the production of bauxite, an ore that aluminium can be obtained from. This is the most common method of obtaining pure aluminium. Aluminium has been used for many centuries and even dates back to the ancient Greeks and Romans, who used aluminium salts on wounds. However, aluminium as we know it today has only been around for about a century. Bauxite, an aluminium-rich material, was first discovered in 1821 in France, and for many years several scientists attempted to purify this into aluminium. Aluminium was first isolated in its pure form by Frederick Wohler in 1827, who is accredited with its discovery in its pure form. 1854 was the first year that commercial quantities of aluminium could be produced. This was achieved by Henry St. Clair Deville, who substituted several of the expensive ingredients of the purification process with relatively inexpensive chemicals. During the next 30-odd years, Deville's process produced over 200 tons of aluminium that was used in ornamental items. The electrolytic process involves passing electricity through bauxite to extract aluminium and produces a much higher yield compared to Deville's process. This was the dawn of today's aluminium industry, and in its first year alone, this process produced approximately 45 tons of aluminium. The first use of aluminium in any structure was the Washington Monument in 1884. The government at the time decided to use a large aluminium cast as a capstone. Since this revolutionary decision, many statues began being cast in aluminium, and the civil industry discovered the potential in this new material. Aluminium use skyrocketed throughout the 20th century in just about all industries, and was widely used as a lightweight alternative to steel.
Physical properties of aluminium. Typically, aluminium is the lightest of all ordinary metals, with a density of around 2,700 kilos per meter cubed. Ultimate tensile strength ranging from 40 to 600 MPa dependent on alloy materials. Hardness on the Mohs scale ranges from 2.5 to 3. Young's modulus of the material is around 70 GPa. Characteristically, aluminium has high ductility and malleability, high corrosive resistance, and high thermal and electrical conductivity. Alloys are usually classed into a series of the main alloying material, with pure aluminium being a 1 series, copper being a 2 series, manganese a 3 series, silicon a 4 series, magnesium 5 series, magnesium and silicon 6 series, zinc 7 series, lithium 8 series. In civil and structural applications, you usually see 5 and 6 series, 5 being sheeting components like facades and whatnot, and 6 series a bit stronger with structural components. Advantages of aluminium are a high strength to weight, long design life, corrosive resistance, it's fully recyclable, can be formed into endless shapes and designs, and it's very strong at cryogenic temperatures as opposed to metal steels. Disadvantages are its loss of strength at high temperatures, and it's susceptible to galvanic reactions and alkali attacks, and its high cost comparatively, as well as strength is still low in comparison to steel.
Almost all modern-day manufacturing of aluminium is a four-stage process beginning with the mining of the ore bauxite. Secondly, the ore is refined into alumina using a method developed called the Bayer process. Thirdly, the alumina is smelted into aluminium via the Hall-Héroult process. Finally, once the aluminium is produced, a variety of alloying, casting, and treatment methods can be applied to turn the metal into an appropriate form for storage, transportation, or use. Relevant Australian standards, for example AS 2848.1, for composition and designations, must be applied at all steps to meet industry requirements. To extract the bauxite ore, typical surface mining methods are applied, and the extracted ore transported to refineries to begin the Bayer process. At these refineries, the Bayer process uses thermochemical digestion to separate the ore constituents and obtain alumina. The third step of smelting, via the Herald Hall process, is extremely and sometimes prohibitively costly, as it runs an enormous amount of electric current through a molten metal mixture of cryolite, alumina, and aluminium fluoride to obtain the liquid aluminium. As a result of the cost, this stage of the process is quite often undertaken in areas with hydroelectric plants to make it financially viable. Finally, the smelted aluminium can be alloyed with other materials to produce the desired qualities, cast into desired shapes, and have treatments such as annealing, quenching, precipitation hardening, extrusion, and rolling to produce desired material qualities. There are three main methods for testing the material properties of aluminium. These are tensile tests, bend tests, and cupping. Tensile tests are governed by AS 1391 and use controlled and increasing tensile loading until failure to determine ultimate tensile strength, maximum elongation, reduction of area, Young's modulus, Poisson's ratio, yield strength, and strain hardening. Bend tests must adhere to AS 2505.1 to AS 2505.6 and use a variety of bending methods to determine modulus of elasticity in bending, flexural stress, flexural strain, and flexural stress-strain response. For cupping tests, there are no set of Australian standards, although their use is approved of by standards, with the involved parties agreeing on the parameters. Cupping tests determine a material's ability to undergo plastic deformation and stretching by forming an indentation until cracking of a material sheet or strip occurs.
In 2011, approximately 17,600 Australians were employed in alumina and aluminium production and bauxite extraction. These projects can have a positive economical impact on the community, generating local employment and government revenue. The production of aluminium requires a large amount of energy. To produce 1 kilo of aluminium requires on average 155 megajoules of electrical energy and emits 8.24 kilograms of carbon dioxide into the atmosphere. In 2010, Australia produced around 2 million tonnes of aluminium, requiring 250 billion kilowatt hours of electrical energy. This large amount of energy becomes a real environmental concern, with coal burning polluting the air and contributing greatly to the greenhouse effect. Aluminium is 100% recyclable, and when recycled there is no loss in material properties. The recycling process benefits the environment, economy and community. It preserves natural resources, generates jobs and saves time, money and energy. The recycling process uses only 5% of the energy requirement and emits only 5% of the greenhouse gases compared to the manufacturing process. Recycling aluminium also decreases mining, protecting local flora and fauna, and decreases landfill. Aluminium is a beneficial material in the construction industry as it guarantees long-term structural integrity with lifetime cost savings. Unlike steel, aluminium is resistant to rust and corrosion, making it a greater material in terms of endurance and overall sustainability.
When aluminum was first introduced in the construction industry in the 1920s, its applications were primarily oriented around decorations and artistic structures. It was not until 1930 when major structures and components in the Empire State Building was the first to be built with aluminum, and ever since, the use of aluminum in the construction industry has been a continual major influence. In the modern age, buildings and civil construction isn't only limited to erecting structures functionally and ensuring they're safe. Consideration for aesthetic designs and economical criteria, long-term sustainability and recyclability are also taken into account and are a crucial aspect within construction. With the introduction of aluminum, many modern architectural concepts and designs can be realized and developed. These designs range from solar panels, facades, roofs and other exterior members to window frames, blinds, doors, and interior decoration and designs, as well as other functional aspects. Alongside the boom of modern architecture, aluminum is also being used to restore historical buildings to preserve its glory. Although traditionally iron and steel has been the primary materials used in construction, the rapid boom and modernization of design and architecture has forced engineers to consider aluminum as an alternative for construction applications. Although aluminum is generally more expensive than steel, it could be more cost-effective in the long term due to its low maintenance rate and zero cost for galvanizing and coating. Due to its minimal weight, it can be stored quickly and conveniently while being environmentally friendly, and its high strength and durability and its aesthetically pleasing design allows for a more contemporary design and style with increased safety. Over time, a significant advancements in technology makes its way into the construction industry based on extensive research, experimentation, and development. It has led to numerous considerable improvements. With technology that allows for the new understanding of the current properties and limitations of aluminium, along with the new understanding of other metals, metallurgy researchers deduced that aluminium has the ability to be alloyed with various other elements to drastically enhance its physical and mechanical properties. Some common alloys are copper, lithium, magnesium, manganese, silicon, and zinc. New current technologies utilizing different combinations of metals allow the properties of aluminium to be tailored to different advantages that are well suited for specific purposes. Alongside alloying, innovation in metalworking processes allows aluminium and its alloys to be worked differently. Heat treatment is a process of metalworking that allows the altering, usually physical but sometimes chemical, of the property of a material. This type of innovation is another way to drastically change the physical and mechanical properties of aluminium to creative advantages. Casting is another innovation of metalworking technique, which involves the process of pouring molten metal into different various shaped molds that contains a cavity of the desired shape, then cooled at different rates, allowing it to solidify. With this technology, aluminium decoration and other functional aspects can be achieved that were not previously possible. These three innovations has allowed aluminium to further enhance its physical and mechanical properties that were previously not possible. Since the early introduction of aluminium as a material into the construction industry, drastic changes has occurred over time. Coming from a material that was merely used for decorative and artistic designs and features, aluminium has been improved to be used in many different aspects ranging from interior to exterior aspects. Many technological innovations has allowed aluminium alloys to be created, each with their own series code along with their own advantageous properties. Many modern buildings and structures around the world, such as the Empire State Building and Enforcement Bridge, has resorted to the use of aluminium given all the advantage properties it possesses. Now, understanding all of these important aspects of aluminium and how it has undergone such drastic changes since its introduction about a century ago, new questions arises. Will technological innovation continue to prove the use of aluminium? And where will aluminium take us now? The future is here.